Okay, thank you very much. So let me start by explaining, for those of you who do not yet know, what this acronym that we have foisted upon the community actually refers to. So LFBOT stands for Luminous Fast Blue Optical Transient, or transients. It is a bunch of adjectives that just describe what it is. So let me quantify these adjectives just a little bit. So by luminous, we historically have meant brighter than a low luminosity supernova, so supernova level or greater. But more recently, we've tried to revise this to be a bit more specific, which I'll describe later. By fast, we mean characteristic timescales both to ride and to fade of about 5 days. Blue, we mean it has a thermal spectrum, but it also has a very high temperature spectrum, which typically means G minus R significantly less than 0. And they're optical because they're discovered by optical surveys, but as I'll describe later, these are also right across the whole EM spectrum. Okay, so if we take those properties and we put them on this parameter space diagram similar to what Ragnhild showed in her talk, they kind of sit in the short time scale, but nowhere near as short as GRBs, luminous, but not as luminous as GRBs, part in the diagram to the top left of the supernova population. Okay, great. So why is that interesting? So this is an interesting region of parameter space because even though they sit next to the supernovae, there's indications that they must have a very different origin in terms of their energy. So if you look back at this plot, the supernovae are in a relatively narrow region, and the origin of that region has to do with the fundamental physics of why supernovae shine the way that they do, which is because of radioactive input from heavy elements synthesized during the explosion. And so this goes back to Arnett in the 1980s, who derived some simple toy models that explain how this works, that tell you that, okay, well, there is a lot of energy input by radioactivity at all times. That's the red curve that you can see here on this plot. That is not actually what the supernova light that we see, because at early times, that energy is being trapped inside the ejecta where we can't actually see it, and it's being lost to adiabatic expansion before it can radiate efficiently. And so the time scale over which it expands to such that the radiation can diffuse out for us to see it gives the rise time scale. And then at late times, there are also losses due to incomplete gamma ray trapping in a typical supernova. So if you want a supernova or a transient in general that's powered by radioactivity to be very fast and very luminous, well, you can increase the amount of nickel, but increasing the amount of nickel also increases the amount of mass overall, because you can't have more mass than you have nickel after all. And so that also increases your time scale. And so there's kind of a fundamental limit that you get, which is shown by the blue region here, where if you have something that is simultaneously very fast and very luminous, it can't be powered by radioactive input. So you have to have a different energy source that is responsible for the predominant energy that we see, okay? As, for example, is clearly true in GRB afterglows, where it's due to a relativistic shock. Okay, so that's a principal definition. What about the actual observation? So this field sort of started in the mid-2000s when larger, more capable sky surveys were looking the sky primarily for other types of things, but we're noticing that among the many transients that were being found, there were some things with characteristic timescales of just a few days and luminosities in or above the standard supernova regime. Typically, they were found at fairly high redshift. Typically, if spectra were taken at all, they were not very good. But there were indications that there was a population of things that didn't match radioactive input that were fast and luminous and had characteristically blue colors. So this was seen first, or at least published first, in the Pan-STAR sample. But these events have also appeared, for example, in the DES sample. There's an example in Kepler with a very nice light curve illustrating that some of them can actually be very luminous and some of them can actually be very, very fast, at least in terms of their rise time. But because of the lack of late time spectroscopy and other types of follow-ups, throughout that decade, most of the previous decade, it was not well understood exactly what they were. But there was a strong hint, because a very easy solution to the problem of the limits of radioactivity to power something like this is just to appeal to CSM interaction. So if you have material around the exploding source, which could be circumstellar material shed by the progenitor before it exploded, or even simply an extended envelope from the progenitor itself, once your fast-moving ejecta from the explosion at the core runs into that, the kinetic energy of the expansion can be converted back into heat at the outside and then be radiated immediately very efficiently producing luminous thermal spectrum, fast rising emission at early times. Okay, so this was seen to be probably the most likely explanation for most of the transients that were seen at the time, but there was not a lot of information to confirm that, because in particular, when you see circumstellar interaction, you should also generally see emission lines, and there wasn't evidence of emission lines in any of those transients to date. So the event that really kicked off the field as we know it now was this event in 2018, which was one of the most fascinating astronomical transients of all time, because it was one of these very fast luminous blue transients, but instead of being at redshift 0.2, 0.3, it was at 60 megaparsecs, which means it could be observed immediately in many ways which were not possible distant transients, most of which were found archivally anyway. So many things about this were realized to be much more extreme than had it even been anticipated from the previous events. Its rise was extremely fast, only 2 days. Its color remained hot, not just at peak, not just after peak, but for months afterwards. So almost very little cooling at late times. It never developed broad features resembling any known supernova or really anything at all. Instead, it developed intermediate features of hydrogen and helium. And then perhaps most importantly, it showed multi-wavelength emission. It showed very luminous X-ray emission, radio emission, millimeter wave emission, which was telling us that this was in fact something quite different from anything we had really seen before up to that point. Okay, so I'll come back to the details of that later. But because this is not a talk on 18 Cow specifically, this is a talk of all the things that we've learned in the 8 years since 18 Cow. I want to also overview what we've learned about the broader population before I come back to explaining those and some other of the peculiar properties that we've seen. So the thing that's really made this possible is yet another generation of very fast, very efficient wide field surveys in the optical, in particular the Zwicky Transient Facility, which has a huge camera, a 47 square degree field of view camera, which allows it to survey basically the whole night sky, or a significant fraction of the accessible night sky, every single night or every other night, to look for things that are fast and to find them preferentially nearby, because it can find everything in the nearby universe visible from the northern hemisphere. Regan Hill also showed a version of this slide in her talk. So this shows the demographics of transients actually in terms of data, not just in terms of colored boxes and all kinds of different transients. And so again, putting that FBOT box as it was defined originally on here, we're interested in things around here, and particularly we're interested in things above this diagonal line that you can see. And what you can see is that after many years of ZTF, we have been able to classify a lot of the things within this diagram. And some of them are more interesting than others. And so I'm going to go one by one through the different populations of things that we do see in there before I then go back to things that are like AT2018 Cow specifically, because what we found is that what were historically referred to as fast blue optical transients are mostly not like 2018 Cow. So some of the other things in this fast luminous parameter space include type 2Bs. Type 2Bs have extended envelopes. They have energetic core collapse produced shocks that shock those extended envelopes, make them very hot. And so they have very early fast rising, fast decaying, shock cooling peaks that are then followed by more traditional rises to a nickel-powered peak. So many people who have worked on kilinovae are more familiar with than perhaps we'd like to be. But what I'll note here is that what can sometimes happen in this class of supernovae is if the nickel is lower than normal, the second peak can be kind of hidden, and in a survey or for a distant transient, you really only see the initial peak, and that might look like a fast blue transient, but if you have deeper follow-up data, you can see the reddening, you can see kind of a shoulder or even a second peak at late times, consistent with a normal type 2B explosion, and spectra look like a type 2B. Okay, what happened there? Okay, there are these ultra-strip supernovae, so Kostov alluded to these in his talk. So these are produced by fully hydrogen strip progenitors, but stripped down to very, very low masses, so only sort of Chandrasekhar mass or a little bit more order mass cores after the companion has stripped everything. These lead to pretty weak explosions and pretty fast explosions because there's not very much ejecta mass, but they're also not very luminous. The luminosity can be boosted a bit if there is some CSM around them, but they tend to be at the bottom end of that FBOT population. And Joshua described the 1BNs in her talk. These are fast transients. that are definitely due to CSM interaction. They also have low ejecta masses, shocking dense circumstellar material, so they share many of the properties that were expected of the FBOT population. Sometimes the lines are not very obvious at early times. They only really develop and get strong in type 1BNs after peak in some cases. And so they can sometimes also masquerade as fast blue transients, but again, follow-up at late time shows that they match the well understood going back 30 years, almost 30 years, population of 1BNs, at least empirically. Okay, we are still trying to figure out exactly what 1BNs are, but they are basically a form. There are 1C broadline supernova that show early interaction. So there was a discussion of one example of this yesterday, 2026 GZF, this Einstein Probe event. If you have a 1C broadline supernova and you have circumstellar material around it for this very fast ejecta to run into shock, that can produce a luminous shock cooling peak. We have seen a few examples of this before, and we've recovered a few examples of that in ZTF as well. It's not very common. And then finally, there is a bit of a mysterious class that is not actually understood what it is called. This only appeared really last year. There was one of them in the ZTF data set, but a few more have been found in other surveys. And they're only found in elliptical, very low or no star formation rate galaxies. But they tend to be on the slow side of the fast transients. They're very luminous, and they cool down at late times. So that's a mystery for another talk. But what I want to talk to you about is the last population in this space, the LFBOTs. So here, very prominently using the L to emphasize that these are particularly luminous, and they're luminous not just in the optical, but across the whole spectra. These are always very fast with rises of only a few days. They're always very luminous. All of them have peak absolute magnitudes in the optical more than about -20. And they don't cool, at least they don't cool very much. They remain temperatures of 10,000 Kelvin plus negative colors out to very late times, out to months. They always show luminous X-ray emission and radio emission, with one emerging perhaps exception to the radio, but we're still working on that one. It's still evolving. Never develop broad supernova-like features at late times, no matter how hard you look. Okay, and so these are the things that are like 18 Cal, and they generally do seem to be something different that is not very much like what we normally think of a supernova at all. At the start of this decade, we only had one and then a handful of them, but now we are starting to actually produce a genuine sample, again, largely thanks to ZTF, largely due to our systematic attempts, particularly led by Anna Ho, who's not here, but is a close collaborator of mine who has written a pipeline and assembled a whole team of people to scan for candidate fast new blue things and to get the follow-up to determine whether they are non-cooling blue, featureless, X-ray bright, radio bright transients, or one of these other many false positives that we get. So there are now many of these. There are many papers on them. I'm not going to have time to describe all the different papers, all of the different events. I will say that there are two posters on some of the more recent ones out here by Natalie LeBaron and by Zoe McGrath. So catch them before they go down tomorrow if you're interested in those. And you're also going to have an overview of a subset of this population in a subsequent talk by Cassie. So I won't talk about all of them, but I will kind of give you an outline of the basic properties that I think are most important for understanding them. Host environments and rates, X-ray properties, radio properties, and then some of the weird things that we still don't fully understand. Okay, so we'll start with the basics. So where are they located? The first thing to understand is they are not located in the centers of their galaxies. So here is the location of the first event, 2018 Cow. It's very nearby, which means there's beautiful imaging from HST, nice resolved galaxy. It's a barred spiral. It is in one of the spiral arms. You can zoom into it. There are star-forming regions around. It's not actually in one of those star-forming regions, though. It's near the star formation, but it's not in something like a bright, young, massive cluster where there's loads of really, really, really massive stars. Okay, so that's a hint of what it might be. That's just a single event. Ideally, like to do a sample study. So there are various sample studies out there. So here's a plot, again, that we're probably going to see again in a couple of talks from Cassie. But they basically trace star-forming galaxies. You see lots of them in dwarf star-forming galaxies. There may be a weak preference towards low metallicity like we see with GRBs and superluminous supernovae, but it's not very strong. We also see them in fairly normal star-forming galaxies up to solar metallicity. And basically, most of these are in more distant galaxies where we don't have nice resolved HST imaging. Hopefully the TAC was kind to us this year, we'll see. But they are at least not from the nuclei. They're coming from star-forming regions and star-forming galaxies. Okay, so that suggests something related to massive star formation and relatively young and massive stars, but not necessarily the most massive stars. Rates. Okay, with the population, we're now reasonably confident that the rate is low. It's about 1/100th or 1/100th of the core collapse supernova rate, 10 to the minus 4. This is of the same order of magnitude as the GRB rate after you correct for beaming, maybe even a little less, or the superluminous supernova rate. So what this is telling you is that it's a rare evolutionary channel. A lot of things have to go right to get LFBOT, an 18 Cal-like event, but you don't necessarily need special environmental conditions like an unusually low metallicity necessarily, or a very dense environment of star formation necessarily. Okay. Okay, now on to the actual properties of transients themselves. So I've emphasized several times that these are not supernova in the general sense of the word. They are thermal transients, but that's about where the similarities to supernovae end. They rise much faster, so this diagram shows a couple of core collapse supernovae with their 10 to 20 day rises and late time nickel tails due to the radioactive decay of cobalt. So they rise much faster, they get more luminous, and then they just plummet after that, and then they plummet below the nickel tails of typical core collapse supernovae. And they don't rebrighten, and they don't show spectral features characteristic of supernovae. The late time light curves are generally, but not, although not always, very simple. You can fit them pretty much as power laws. They're very luminous. So 18 Cal amazed us with how luminous that it was at peak. So it is the less luminous of these two things here, and you can compare it to the superluminous supernovae that Ragenhill described in a previous talk. At peak, the Cal was more luminous than a typical superluminous supernova, and since then we have found more events that most of which are actually more luminous, and this latest event from a couple years ago, AT 2024 WPP, which many of us got very excited about, is one of the most luminous transients we have ever seen. It didn't remain luminous for more than a week or so, but at peak it is one of the most luminous transient events that we've ever seen in the sky. More luminous than any supernova by about an order of magnitude. If you total up the radiative energy output for these most luminous events, you can get in excess of 10 to the 51 ergs, comparable to the whole available supernova energy budget after neutrino losses. So you need an intrinsically energetic event to fuel one of these things. Temperature evolution. Okay, so as I've already mentioned, they start off really hot and they stay hot. So typically you're looking at temperatures in the first week of 30,000 Kelvin. They cool slowly, but even if you look at them months after, you're still seeing temperatures of 15,000 Kelvin at the surface, at the effective photosphere. So something is keeping the surface specifically hot. Very different from an ordinary supernovae, which cool as they expand, understandably, because they're being diluted, they're expanding adiabatically, and they're only kept hot by the slow diffusion of radioactive input from the inside. So the whole physics of the photospheric evolution is really genuinely quite different. And that's even more evident when you look at something like the blackbody radius for the two best well understood, well studied of these events so far. Ordinarily, supernovae, their blackbody radius expands. Now, it contracts in the ejecta frame because it is, as the ejecta becomes optically thinner, the photosphere moves inward in the ejecta, but the ejecta is still expanding out at supernova-like velocities, and so the photosphere always expands until very, very late times where basically the whole thing is becoming optically thin and you're just seeing the core. LFBOTs instead only show expansion for a few days, and then immediately the photosphere starts contracting, even though it's remaining optically thick, which is a very difficult thing to accomplish physically, because generally the reason that the photosphere recedes is it is becoming optically thin, but these are retaining optically thick spectra even though the photosphere seems to be receding. So that was a very puzzling observation early on. I'll get back to our interpretation of that in a bit. Early spectra are basically featureless. There are indications of these broad undulations indicating very high velocity material. We have not successfully, for sure, identified any lines in those yet, but they do seem to be there repeatedly in different sources, which basically just tell us that it's high velocity material. This continues even into the far ultraviolet, so I was very excited to get a full far ultraviolet spectrum of 2024 WPP 2 years ago, expecting it would be one of the things that would resolve the mystery, and it was also completely featureless. So this is telling us that something above the photosphere is keeping all the things that would normally be responsible for our spectral lines likely ionized, because we do not see these very strong resonance transitions that are normally dominant in UV spectra of supernovae. There's a lot to be learned from other wavelengths. So particularly in the X-rays, these are very distinctive sources. Their X-ray luminosities are comparable to those of GRB afterglows and orders of magnitude above even the most energetic supernovae. So you can see this schematic diagram here, which shows light curves of LFBOTs compared to some real light curves of different classes of things. And they're very luminous, and they also show interesting structure. So there's short-term timescale variability, at least out to about 20 days in 18 Cal and perhaps in 24 WPP as well, followed by a sharp drop at late times. Some other events are even more luminous. We don't know for sure if they show the same variability, although there are hints that they do. So there's a lot of energy also coming out in the X-rays, although it doesn't dominate the bolometric luminosity until late times. X-ray spectra are also interesting. So in Raf Marguti's paper on 2018 Cal, she showed that it is consistent with having an iron line and a Compton bump. This is a very characteristic spectra of what you see from accretion disks around black holes and other systems, which is a strong clue of what is producing the X-rays, as is the fact that it's very luminous and variable on fairly short timescales. In the two events in which this can be done well, the X-rays start off less luminous than the optical, but they kind of evolve to match at late times and then seem to suggest that they co-evolve from then on. Okay, so how do you explain all this together? So I puzzled over this for a long time, but of course the theorists, they're very smart and they have figured out a good model a long time ago. And the likely interpretation for all of the things that I just described to you is a picture in which you have a very energetic central engine that is producing lots of X-rays from accretion or some equivalent high energy process. And it's the accretion disk around that source is sending off a fast wind at 0.1, 0.2 of the speed of light in all directions. And that wind is being energized by the X-rays from below. And that is also keeping the wind ionized. And so because the wind is heavily ionized and because it's fast moving, we do not see the normal features that we see in ordinary supernova spectra. And instead, we see a thermal spectra that is the thermalized X-ray photons. And the luminosity basically just tracks the slow decay in luminosity of the central energy source. And shielded it by this fast outward moving wind that slowly tapers off with time. Okay, so now there's also a lot that can be learned from the radio, because in addition to having energetic emission from the central engine, there is also a lot of energy being produced when the wind and the ejecta is running into the material around it, which gives us a strong clue. So these things are very strong radio emitters, and they have very distinctive radio evolution. Unlike GRB afterglows and unlike supernovae as well, they tend to show very slow rises, peak at hundreds of days, and then suddenly shut off. They have very sharply declining late-time light curves. And we see that in basically every event, and it's quite a big sample now. Again, I think Cassie will say more about this. We can use the radio SEDs to characterize the shock properties and characterize the density profile of material of which the ejecta is running into, which is an important constraint in the progenitor. And that tells us the ejecta are moving very fast, which we knew already from the optical, but it's good to have that confirmed. And it tells us that the CSM around it drops off very sharply with radio. So there's a lot of material close to the progenitor. There's not very much material further out from the progenitor. And there are even indications that there's kind of a drop off at around 10 to the 17 centimeters when the radio shuts off. I'll skip over talking about the NIR excess since I'm already running out of time. But I think what this is pointing towards is that some sort of mechanism that reliably produces a lot of material close to the transient on the same time scale in the same way shortly before explosion, which could be some sort of common envelope activity, but it also could be another model. Okay, now to wrap up, I want to say a few things about the peculiarities that we have not really fully explained yet. One of them is the spectroscopy. So the spectroscopy for the three events in which it's been possible at late times is dominated by hydrogen and helium, with some evidence of helium enhancement compared to, say, a solar composition. So that's a clue. But the profiles are really weird. They show intermediate velocities. They're different every time. One of them actually shows a double peak profile with a separation of several thousand kilometers per second, even though each component is individually narrow and that's stable with time. There are net blue shifts in the line centers on two events. Very strange line profiles telling you that there exists a component of dense material in the system that is very asymmetric and moving very fast compared to the systemic frame. And then in one event, still just one event so far, the only event that's going to be done because it's the only one close enough, at very late times, hundreds of days after declining sharply, it plateaued and turned into an extremely hot 100,000 Kelvin, 10 to the 7 solar luminosity, steady but slowly declining hot blue source. Too faint to get a spectrum, but bright enough to characterize the UV properties with HST. This has never been seen in any transient ever, so it's almost unprecedented. It is unprecedented. Also, X-ray is consistent with that, which I'll skip over. And then by far the weirdest thing that I've ever encountered in my entire scientific career, which if you were here for Rahul's talk yesterday, you've already seen a teaser of, but let me actually show you the imaging that clued us off to this. So this was just getting some late follow-up of not even a particularly close or well-observed or at the time interesting LFBOT, just some due diligence. Let's make sure it's faded away and get some template imaging for host subtraction later. And then the observer, Ping Chen, noticed that over the 5 exposure sequence, the source was actually brightening and fading within those 15 minutes of the observation. And so this was the discovery of fast optical flaring. So those are the same 5 exposures, this time image subtracted in the bottom row, showing clearly there was something appearing, becoming 21st magnitude, and then going away again on that time scale. So we observed this with many more telescopes. We confirmed it. There's short-term variability during the flares on timescales of less than a minute. There are long flares, there are short flares. There's all kinds of interesting flares. We would have liked to do more, but it was a very difficult time to get observations right before Christmas, and the source quickly went behind the sun. But we did recover a bunch of them and characterize them. They have a range of time scales, but they, in the most luminous cases, approach the same luminosity as a transient at peak, or the luminosity of a supernova, but time scales of seconds to minutes. So nothing like that has ever been seen before. And one FBOT did this on time scales of 1 to 4 months after the initial explosion, and then it stopped. They didn't continue the following year. Okay, so so we've been getting many clues to the progenitor. Okay, I won't go over them here because again, I'm short on time. There are lots of ideas for what it could be. I think most of these do not predict the observations that we see particularly well. I think there are 3 models that most people would say are still in contention, and these are a very massive star that's collapse has failed, and so it's producing some sort of fallback supernova, maybe with a weak jet. Disruption of a source by an intermediate mass black hole, maybe a white dwarf, maybe a solar mass star, but disruption by an intermediate mass black hole, so it's TDE-like but faster, or a binary merger between a black hole and a companion star. And so there are various ways to achieve all these scenarios. I think we are still trying to figure out which one works. If you look at the evidence that I described, some of them work better with some of them work better with the other. I think the star black hole merger binary model probably works the best, but it also makes the least specific predictions. So that's not necessarily evidence conclusively in its favor. So there's more work to do. So to sum up, this is a genuinely new phenomenon. We don't know what produces it yet. So if you want something mysterious and unsolved to work on, this is a very good choice. There are a shared set of properties that we see over and over again. They're hot and fast, they're radioluminous, they're in star-forming hosts, but there is also some diversity as well. We are almost certainly engine-powered. The engine is probably an accreting black hole based on the need for this wind and this energy input. And there is confined CSM around that has to get there somehow, perhaps from a binary, perhaps not. And so there's more to be done. We need more data, and we need more models.
Thank you, Dan. Any questions?
Thank you very much for the interesting talk. The very, very last thing you just said is we need more data, but observers love saying this. Can you be more specific? If you could snap your fingers and get one thing that you definitely want to see to determine what's going on here, what would it be?
Oh, if I have to choose between one thing, now that's hard. But I did prepare a wish list, which is a realistic wish list, I think. So I don't think we know what is going to cause the breakthrough. So we have to try things we haven't tried before in terms of observations. So I think looking before FBOTs, if we have deep LSST style imaging series, and then we see an LFBOT from the same location, we can go back and look if there is variability, because of, that CSM has to get there somehow, and being able to unambiguously show on what time scale that happens, that will help. A much larger sample will allow us to do more specific predictions in terms of what you need to produce certain types of systems. Is it a very massive star? We should be able to rule that out with a big enough sample because those should only be happening in certain places. I think most likely the thing that is going to be the breakthrough, as has been the case throughout the discovery of LFBOTs, is going to be something that will surprise us. So I think we just have to, but as new capabilities become available, we deploy them and we see what we find.
Sure, thank you.
Yeah.
Yeah, I'm confused with 2 points. One is you said that the optical spectra is still optically thick at a few days, even when the RBB is declining. What do you mean the optically thick?
So optically thick means it is continuum dominated and consistent with a black body in its broad shape. Yes. So the photons that are being produced by whatever the true energy source is, which is probably the central engine, but whatever it is, are being thermalized before they escape and reach us.
Okay, another question is why you say the black hole star merger model cannot explain the UV plateaus.
Yeah, so I didn't have time to go into that. Yeah, so that was the one X on the star black hole merger model. So the UV plateau is not well explained, but there do exist models in the literature for tidal disruption events, which and observations of some tidal disruption events, which show that they show plateaus at late times, and that plateau is more or less proportional. It occurs at about the Eddington luminosity, so it is a probe of the mass. And the UV plateaus, if they are due to this phenomenon, imply masses that are higher than a stellar mass black hole should be and closer to the intermediate mass black hole regime. So that has been one of the evidences in favor of the IMVH-TDE model. But because we don't really know for sure what causes the plateau, that's not particularly conclusive evidence.
Thank you.
Okay, I think we have to move on, but yeah, thanks again, Dan. Okay, and our next speaker is Cassie Sevilla, who'll be talking about multi-wavelength analysis of 6 LFBOTs. So yeah, over to you.
Thank you. I'm Cassie, a PhD student at Cornell University, and here I will present a subsample of 6 luminous fast-boot optical transients, though I will spoil a little bit and say that one is a little bit more unusual than the others. So this slide should look familiar to you because you saw it 30 minutes ago in Dan's presentation, but just in case, I can go over the acronym of what exactly LFBOTs are. They're luminous, which means they're brighter than around -20 magnitude in the optical. Fast means that they're optical light curves. They have like a half maximum timescale of about less than 10 or 12 days. Blue, so that means their G-band detections are brighter than their R-band by at least like 0 or 0.2 magnitudes. And optical transient refers to the fact there are transients discovered in the optical bands. So these objects are superficially similar to supernova. They're extragalactic. They have roughly similar absolute luminosities. However, LFBOTs also have that bright X-ray and radio emission, which is seen in a lot of members of the sample. And so that makes these very data-rich, very unusual transients. And there's also the fact that because their light curves are so fast, it's very hard to explain the optical emission just from decay of radioactive nickel. So as just an overview of the current mostly well-accepted candidate theories for what an LFBOT actually is, there's a single star's death that causes some sort of failed supernova. There could be a tidal disruption event by specifically an intermediate mass black hole because these objects are usually found at large offsets from the nucleus. Or there's some sort of merger going on. Could be a black hole in a Wolf-Rayet star, could be a neutron star black hole in a main sequence. There's a lot of different scenarios making lots of different predictions. And So far, the picture is still a bit hard to distinguish between these three on which causes LFBOTs in general. So I'm here to present 6 CTF LFBOTs, one of which, AT2023 FHN, has already been extensively analyzed and published by Ashley. I'm just adding on some extra data on his paper. And in this talk, I'd like to specifically focus on the optical UV light curves and the radio and millimeter emission, and furthermore, modeling the radio millimeter emission as a result of synchrotron radiation, because these, I feel, can give us the most thorough conclusions from this subsample. So as I have also included a figure of the offsets here, and you can see for most of these LFBOTs, they do have a visible offset from the host galaxy center, except for the bottom right one, AT2024 AHP, which is a little bit strange, and I will talk a bit more about it later. So in the optical, their optical light curves of this subsample mostly mirror the luminosities and the rise and fading timescale of past LFBOTs. Shown in gray is the light curve for AT218 COW, the sort of prototypical LFBOT. But of course, again, on the bottom right, there's AT2024 AHP, which initially fades relatively fast, which is why we classified it as an LFBOT in the first place, but then has a very extended long plateau, which is strange. But as for the rest of them, the optical properties are similar, which makes sense. Furthermore, the radio emission of this subsample is remarkably consistent. So this is the luminosities at 10 gigahertz. And you can see they have roughly the same luminosities, roughly the same like rise and fade timescales as well. And the radio emission of LFBOTs is best understood as a broken power law resulting from self-absorbed synchrotron radiation. Essentially, the peak is somewhere between 10 gigahertz and 100 gigahertz at early times. It slowly brightens, and then it reaches at its brightest radio luminosity when its peak is at around 10 gigahertz near 100 days, and then the peak keeps going to shorter frequencies and the overall SED fades. And again, you can see in the pink line here that AT2024 AHP does stand out a little bit because its peak is a little bit later and delayed compared to the others. But ignoring that one outlier, for example, we can model the radio emission as a result of synchrotron radiation, and we can get some conclusions about, say, the shock velocity, the shock energy, the shock density. And because the radio emission is fairly similar across the sample, it makes sense that the parameters we get from our synchrotron analysis are all fairly similar. And this points to there being a consistent dense circumstellar medium surrounding these explosions. So the reason I focus on the optical and the radio is because they probe two different regions of this transient. The optical, we observe on a timescale of tens of days. It comes from the photosphere, which is up to hundreds of AU in radius. However, the radio we observe on timescales of hundreds of days, and by then the shock has traveled much further away from the progenitor, and it probes distances up to like 10 to the 3 or 10 to the 4 AU away. And the reason this stands out is because these properties are fairly similar across the LFBOTs in the sample. It's not altogether obvious how to link these two. It makes sense the optical is similar because we are selecting for certain optical properties, but for the radio to also be similar while probing a completely different region of the transient is fairly interesting, and it's probably what I think to be the best clue of what could possibly be causing these things. So from this sample, because of the fact that there is a consistent CSM, a presence of a consistent dense CSM, this would favor a scenario that can consistently cause some sort of enhanced mass loss and produce similar conditions surrounding the explosion. So one example could be a merger scenario where during the process of the merger, some mass is thrown out in an asymmetric fashion, and that mass can give rise to the dense CSM that later would produce the synchrotron radiation. Now, there are some caveats to this general analysis if you want to extend it to the entire LFBOT sample. Mainly, there are optical selection effects because we are discovering these things in optical surveys. So this would naturally force all the optical properties to be similar. And we also assume, we also do our synchrotron analysis, assuming a non-relativistic shock with non-thermal electrons, which doesn't change our qualitative conclusions, but can affect our quantitative conclusions on what the densities, what the energies are. I know there's some work done by Ben Margalit, Jakub Klencki, and other collaborators on trying to extend the synchrotron model. But now finally, I'd like to talk about AT2024 AHP. So as I mentioned, it looks like a nuclear transient. It has this very long, unusual plateau, at least unusual for LFBOTs. And its radio evolution is very different. And specifically, I can compare AT2024 AHP with a more standard LFBOT in AT2023 VTH and their radio SEDs. So we can see in AT2023 VTH, it tends to reach a peak at around 100 days. The peak frequency is around 10 gigahertz, and then it fades. Meanwhile, for AHP, it still exhibits bright radio emission up to 400 days after the explosion, and its peak frequency is still well above 10 gigahertz, which is definitely unprecedented for this class of transients. So from these strange properties, there's the idea that maybe AT2024 AHP is more of a traditional TDE. After all, these supermassive black hole TDEs are by definition often nuclear transients. They can have slower light curve fades than LFBOTs. And some of these TDEs do have late time radio brightenings. And this properties do tend to generally match AEHP, but there are a couple, there is one unusual discrepancy. And that's the fact that in these TD brightenings, I've shown an example with from Itai's Faradi's paper on a 2024 TVD. The peak frequency of the radio emission tends to move to frequencies shorter than 10 gigahertz really fast. Meanwhile, for AHP, its peak frequency is still like 10 to 20 gigahertz for an extended period of time. So it's not an altogether complete match. So since the radio emission is very mysterious, we did obtain a European VLBI network observation. And I'd like to shout out Stefano Garatana for helping me a lot with sending proposal and reducing the data. And we did find that the radio emission is coming from a place consistent with a point source, which rules out superluminal motion. We can't get better constraint on the possible velocity. And we are aiming for another epoch to look for apparent motion if the radio emission of AHP does remain a luminous for an extended period of time. So finally, I'll just leave off with a summary. So most LFBOTs tend to have similar radio light curves, similar radio properties, which implies that a dense medium is sort of almost ubiquitous across the sample. And I would say it does slightly favor a merger scenario, but you can definitely explain those properties with some alternative theories. However, there are clear outliers with special properties. For example, AT2024 AHP, could it just be a special LFBOT or unusual TDE? Maybe it's something intermediate between the two classes, or it's just something else entirely that just happens to share some of the same properties. So there's most definitely unexplored diversity in the sample, which is made difficult by the fact that these transients are relatively rare. So this can be alleviated by more sensitive surveys like Rubin, or maybe developing new discovery pathways to alleviate our selection bias. So maybe we have ultraviolet high cadence surveys like UVEX, or perhaps X-ray surveys in the future that are sensitive enough to find these. And with that, I'm happy to take any questions.
Yeah.
Yeah, hi. I was confused about your comparison between the 2024 AEHP and 2024 TVD, because I remember 2024 TVD is an off-nuclei TDE, and you said that 2024 AEHP is the nuclear transient. So why do you compare to?
I just tried to pick a representative SED for the TDE radio brightenings. Like I found that these TDE SEDs do have that characteristic of moving to frequencies shorter than 10 gigahertz. I wasn't trying to match them specifically one-to-one. This was just a sort of sample TDE SED, just to show the biggest difference I find from AHP and the rest of the TDE sample.
Oh, okay. Yeah, thank you. Yeah.
Any other questions? Yeah.
Thanks for the nice talk. Do you have any constraints at all on the mass, the baryon loading essentially effectively of the environment from the radio observations, or?
I don't think so. I don't think we've performed that type of analysis just yet. Is it sort of the how much mass would be in the shock.
Yeah, divided by wind velocity or some sort of outflow velocity.
Gotcha. I don't think so. I think the synchrotron analysis we do is with the density of the medium, but I'll definitely take a look and see if we can get the actual shock mass itself for mass.
Let's thank Cassie again. Okay, our next talk is from Quentin Pognan, who'll be talking about LFBOT light curves from a compact object central engine model. Over to you.
Hey, so thank you for sticking around to the last session and to my talk. I'm a postdoc at the Max Planck Institute for Gravitational Physics, and we've heard a lot why LFBOTs are exciting objects, and they're particularly exciting to me because it's a new type of transient that I'm working on. I'm usually a kilonova guy, and it's nice to have objects with data. So without further ado, let's move on. So we've had a great overview from Dan Perley about various LFBOTs, their properties and such. I just want to summarize a few of the observed ingredients that I think are common among all these objects and things that we ultimately want to reproduce from the modeling side, which is what I work on. So from observations, any model that wants to explain why LFBOTs look the way they do have to, reproduce several things, which are usually found in the name or the acronym of the object, right? So for instance, we need to reproduce the fast evolution of light curves. At least in the optical, let's say that's a rise time of 1 to 2 days, and then various kind of different evolutions as we saw past the peak. We also need to produce an abundant amount of X-rays and hot UV light that is usually well fit by some kind of hot black body. And by hot, I mean going from something like 30 to 40,000 Kelvin, and then down to 10 to the 20,000 Kelvin. So that's still remaining very hot for an extended period of time. We saw that the LFBOTs also have radio emission, which we inferred to be from very extended but very dense CSM, and importantly, a density profile that doesn't really fit the classic kind of power law expected from a simple wind mass loss. So another mysterious ingredient there. Aside from producing all these different emissions, in X-ray, in radio, and optical, you also need to have the total kind of amount of emitted energy being correct, right? They're luminous. You need a lot of energy. But not only do you need a lot of radiated energy, you need the ratios between the different components to be kind of correct, right? So for instance, something that was looked at a lot in COW and WPP was the ratio of X-ray to UVAR, right? So we typically have UVAR luminosity dominating, and at late times, they come together. So a model needs to be able to reproduce that as well. There's also some extra observations that don't necessarily show up in every LFBOT, but if you want a model that can explain the whole class of them, they need to somehow be able to include these. For instance, the emergence of this Compton or hard X-ray hump that Dan talked about in 2018 COW, the infrared excess that is now seen in COW and WPP. And by excess, I mean excess compared to the hot black body that is usually fit to the optical light. Some of them also have variability in X-ray and optical light curves, not necessarily on the same timescales. X-ray sometimes on 1 or 2 days, optical perhaps several days or a week. And of course, ultimately, each of these kind of different emission components has some sort of spectral evolution. And this is perhaps one of the toughest things to explain is, how do you produce a consistent model that can explain, the weird way the radio is behaving, the kind of emergence and disappearance of this hard X-ray hump, and then the progression of the UVAR spectra from completely, hot, featureless to suddenly broad lines moving at 0.1 C, and then the emergence of these weirdly shaped narrow lines. So that's a lot of ingredients, and it's very hard to produce. But as we saw, we do have some models that have attempted to do so. And I'll preface this slide by saying this is not a complete list. I have not included all the references. I am deeply sorry if I've missed anything important. As we usually do when a new kind of class of transient arises, we try to find out if some weird supernova can reproduce them. And here I've just kind of grouped every, supernova type into one overwhelming umbrella. Let's say whether it's magnetar-driven, as is shown in this little graphic here, or a failed supernova. But essentially some sort of stellar collapse model. Pick your favorite type. We just heard about the Wolf-Rayet or evolved star black hole neutron star merger, originally suggested by Brian Metzger in 2022, which is a favorite model of many people here. We also have various TDEs or stellar disruptions of various mass ratios and flavors. Again, a few references there. And then the pure kind of CSM interaction models, for instance, like recent work by Govin Segal, where you don't really need a central engine or anything. You try to explain the whole thing through one single kind of shock interaction. So what kind of goes into these models, right? Well, many of the models have similar ingredients, right? If you look back at the previous slide, which I'm not going to flip back to, but you get the idea, many of these models have some sort of compact central object that's providing an energy input. We need some dense CSM for the radio, and you have one or several ejecta component. And so what we want to do with this new project is, ask the question of, okay, if we bring all these ingredients together in kind of a unified physics framework, can any of the models fully, in brackets, reproduce observations? And I do want to say this is somewhat different to previous work, say by Conor Oman and Nikhil Sarin, that brought these models together in Redback and tried to fit these light curves, say from a statistical perspective. We really want to model the underlying physics and see if we can reproduce observations. In our case, we'll focus on models with compact central engines, and we're not going to do anything involving spectra, at least not yet. So the methodology for this. We are basing our work on public code called GRB, which is not actually for gamma ray bursts, but I did not name it, so I'm sorry. It's actually originally for magnetar-driven ejecta in neutron star mergers. And the idea was to produce X-ray and so UVAR kind of optical light curves. So as you can imagine, that's a pretty convenient place to start when we're looking at LFBOTs, specifically for modeling X-ray and optical light. If you're interested, the link to the GitHub is there. There's also a recent paper by collaborator Clara Place on this, and the equations are based on the work by Sun et al. 2017. In brief, we take this kind of public code, we modify it a bit to have different central engines, so not only a magnetar, maybe also an accretion disk, a black hole, etc. And we also aim to improve the physics of most existing semi-analytic models, again, in a kind of consistent framework. So, maybe we want to allow a reprocessing of X-rays from the central engine to impact not only the internal energy of ejecta layers, but also kind of the kinetic energy, their dynamics. Perhaps we add some corrections where appropriate. And something which is actually the part I'm working on is also to consistently add other emission components. In this case, let's say a dust echo. More on that later. So I'm going to show very, very preliminary results from last week. So, again, keep in mind this is preliminary and ongoing work, and this was actually just mostly testing a few of the basic models. So the first thing we wanted to do, of course, was to see, okay, can we reproduce one of the existing models in literature, in this case, the Wolf-Rayet black hole merger model from Brian Metzger. And okay, yeah, you can see here, it does a pretty good job of reproducing it. I apologize for the lack of X-ray data on this plot. I somehow could not find the luminosities anywhere publicly. So, if you're willing to send those to me, please, thank you. But something that I want to point out in this model is that small factors that we usually like to ignore as astronomers and astrophysicists can sometimes matter. So for instance, in the classic model here, the dashed line, which is the kind of a shock, slow-moving shock component, if you know the model, is assumed to be expanding relativistically. But actually, if you treat the slow-moving ejecta as non-relativistic and you add your little factor of 2 to the adiabatic expansion, you see that that shock component drops a lot sooner, and you don't get that bump in the UVAR that you really need. So sometimes, yes, small factors of 2 must matter, and we will try to take those into account. Another thing that we tried was asking, okay, what if we take the same kind of merger model, but instead of having a black hole, we put a magnetar in there? Because why not? It's fun, the code was meant for it, and it's a parameter space we want to explore. So naturally, if we have a magnetar in there, it's a different form of energy injection than just a pure black hole and accretion disk. It's a lot more energy. But interestingly, we actually can manage to recover a fairly reasonable fit to the bolometric UVAR light curve without messing around or fine-tuning parameters too much. Of course, in this case, the X-ray luminosity is way too bright at late times. But the main point I want to stress here is that we can reproduce the UVAR pretty well, and I'll bring that back in a few slides. We also considered a magnetar supernova, which I guess from the previous slides has already been ruled out as a theory, but we're being agnostic to that. In this case, it's very simple, single ejecta component. We stick a magnetar in there, and we also consider radioactive nickel decay in the ejecta. As before, we can find a somewhat decent fit to the UVAR, particularly at early times. At late time, we overpredict the optical luminosity due to radioactive decay. But so my main point in showing you these three kind of basic models is that you can do a surprisingly good job of reproducing, let's say, the broadband, or rather bolometric luminosity evolution with a few simple parametric models. And what this means is that you won't be able to tell which model is right if they can all fit the data, right? So one idea is then to add other emission components self-consistently. So a couple of the LFBOTs have now shown an infrared excess, possibly an infrared dust echo, as was suggested by Metzger and Dan Perley in 23. Now, the property of this infrared light will depend on, the emission of the central source, the UV, of course, the CSM and dust properties itself. And so what I want to do, and this is the part that I'm working on personally, is that I want to take dusty CSM with the inferred properties, say, from the radio in terms of density and all this, and I want to model the infrared echo associated to this consistently. For this, I'm basing my work on a paper by Liu et al. 2016, which was actually for dust echoes from TDEs, but the physics principle is the same. I have a layer of thin dust shells. For now, it's a very simple kind of spherically symmetric concentric thing just to check. But in essence, for a given kind of central UV source, I want to calculate the temperature and dust grain size for each layer of thin shell, get my emissivity from this, and then do ray tracing with the infrared light to really see, okay, ultimately, can we reproduce something like the dust echo? This particular plot is again from Metzger and Perley 23, which did a preliminary version of this. And you can see that, okay, the models can reproduce some part of the observations, but it's not, it's not an amazing reproduction, if I'm allowed to say that. And so the idea is that, okay, if we self-consistently model the UVAR, the X-ray, and then add things like this infrared dust echo consistently, can we actually reproduce observation of several different components? If not, does this mean, okay, that the dust echo idea isn't actually working? Does this mean, for instance, that we need to consider something else, like a pure shock model as suggested by the recent paper from Goveri and Sahil? So with that, I'll just leave you with my conclusions. We see several commonly observed features in LFBOTs, and accordingly, most of the models, or many of the models, have similar ingredients. Our work, we want to focus on central engine-driven models, group all these kind of, semi-analytic models into a single framework with a single set of consistent physics, and see basically what happens. Thank you.
Thank you. Any questions? Cool.
Thanks for the nice talk, Quentin. I'm just wondering whether you've thought about 2D effects. So if you had actually had a 2D code or 3D code, if you could, because I'm wondering if you have like magnetar blowouts or things like that, how could that affect things?
Yeah, so we don't really model multidimensional with this current code. The kind of like closest thing we have is we have a viewing angle parameter that we can adjust. And so when we're modeling kind of like two ejecta components, we can add like a small correction factor to the emission for that. But we haven't actually considered things like magnetar blowout effects. Yeah, I think that would probably be follow up on a more kind of detailed thing. The aim of this is really just to have group simple semi-analytic models into, again, a consistent framework and see what we can get from there.
And maybe one more.
Yeah, I was wondering whether the magnetic model can explain the blue optical bump in the hard X-ray. Blue X-ray bump, sorry. Blue bump.
The hard X-ray bump. Yeah, so we haven't gone into that yet. Probably not would be my guess. But so the thing in the current kind of like preliminary magnetar model that we have, so not the magnetar supernova one, but this one, is we actually do still have an accretion disk powering this. So this is really the Wolf-Rayet black hole merger model, but without really justifying how or why, we actually say, okay, what if the black hole is a neutron star that is also a magnetar? So in this case, it would probably require some sort of fine tuning, or we'd have to find the parameters. But the idea is, if you would have an accretion disk around the magnetar and it were to accrete enough mass, it could collapse to a black hole, in which case you would have a remnant kind of accretion disk still around this black hole. And if the hard X-ray hump is from an accretion disk, then it's just a matter of timing such that you do get the hard X-ray hump. So it's not something we've looked into yet, but I think it would still be possible within the model.
Your explanation is it's no longer a magnetar, it becomes a black hole, and then it's solved.
Yeah. So in this case, this is a first test case just to see what happens when we do put a magnetar. So in this case, it doesn't really collapse, and you can see the X-ray just keeps going, right? In reality, this is one of the upgrades we're going to do to this public code, is to also code in a collapse time for the magnetar. So at some point, which we'll calculate, we'll say, okay, magnetar is gone. You've only got the accretion disk left. What happens there? Again? All right, and our next talk is from Jakub Klencki. Yeah, and this talk is from Jakub Klencki. It'll be on LFBOTs as failed gravitational wave sources.
Yes, thanks a lot. Okay, hi everyone. I'm Jakub Klencki. It's nice to meet you all. And I want to continue speculating about the possible progenitors of LFBOTs. And in particular, I'd like to propose a scenario in which these black hole and helium core mergers, the origin of those could be quite closely related to the origin of gravitational wave sources that LIGO Virgo sees. And so I'll take advantage of the fact that the previous talks already greatly introduced what observationally are LFBOTs. And I always start with this cartoon that sort of presents what are the components that we need or physically are there. So we have some central engine that's a compact object likely accreting from a disk, rather long-lived disk, to explain this a couple of years after the peak as well. And then all of this is embedded in a large asymmetric dense CSM. That's about 100 times denser than what you get from just the wind of a massive star. And this CSM is extending to like 10 to 16, 10 to 17 centimeters. And so this is about like a few times the size of a red supergiant, basically. And they've in multiple ideas tried to put this picture together, and other people mentioned it already, that broadly the scenarios can be distinguished into those involving a single very massive star, a tidal disruption event of a star by an intermediate mass black hole, and various types of scenarios that in one way or another involve a binary star, usually merging. And so this is what I'd like to talk about. This is the type I'd like to talk about. And in particular, we consider systems in which there's a stellar mass black hole, a massive star companion that are interacting with each other. But at some point during this interaction, it becomes dynamically unstable, such that the black hole merges with the star and eventually its helium core as well. Okay, so it all starts with systems with a black hole and a massive star companion. Traditionally, those would be X-ray binaries, such as Cygnus X1. But now we know as types of systems that are actually currently not interacting. The mass transfer hasn't started yet. These are the dormant systems. And there's a lot of excitement about those in different fields, and particularly because the prediction is that we should be getting dozens of more of such binaries known in the Milky Way and nearby galaxies, even by the end of the year with the next Gaia data release. So now there's a handful of those plotted here in the diagram of the orbital period and the mass ratio on the two axes. And the prediction is that instead of a handful of these, we may be able to understand the underlying population, how it's distributed in this parameter space. And so the key question for the evolution of those is when the mass transfer happens, whether or not it'll be stable or unstable, and what would drive the instability. And currently, probably the best tool we have to address this is to simulate the evolution of such systems with a 1D binary evolution code such as MESA, which allows us to model how a star responds to mass loss. And so we can track the size of the star with respect to its Roche slope. And we can see if it's growing too big, then that's starting to trigger dynamical instability and likely a merger. And so now using MESA, what we can do is we can go back to this parameter space and forward model the evolution of such systems to try to assign them to some final fate. And this is what now been added here is this grid of rectangular rectangles, color-coded according to what we predict would be the final evolutionary state. We start from a black hole, the fiducial black hole mass of 10 solar masses, and a massive star companion that's from something like 20 to 100 solar masses in this parameter space. And then we see various types of outcomes. Yeah? So up here in red, we have systems that do become unstable because the donor is a red supergiant star. So if you're familiar with common envelope, this is the guys that go through classical common envelope. But then in yellow, we have systems in which the mass transfer remains stable and just formed two, a black hole and maybe another black hole neutron star in a wide orbit that is not going to merge within the Hubble time. In green is the reason why this plot was made. There's a lot of work being done in the context of LIGO-Virgo sources to predict which of those binaries will form binary black hole mergers. But then always what people find, including us, is this parameter space next to it, where the mass transfer becomes unstable and likely the black hole merges with the massive star. It is no accident that this parameter space is next to one another. Basically, for LIGO sources, we want to shrink the orbit during mass transfer sufficiently. But then it turns out that if you reduce the separation too much, this is the physical trigger for instability in those systems. So it's a natural prediction that a similar type of black hole massive star systems will either produce a LIGO source or some sort of transient from a merger, right? And so what's also interesting in this instability is that it doesn't happen over time immediately. So if you plot what's the mass transfer rate in a couple of examples of those systems from the grid as a function of the amount of transferred mass, we have one example that's coming from the instability leading to common envelope. And you can see that only a little bit of mass was transferred before the instability happened, so it was launched quickly. But in the ones we are thinking of, there's actually a pretty long phase of essentially stable mass transfer where we lose like half of the envelope before eventually the mass transfer rate goes up and becomes dynamically unstable. And so this has been known as delayed dynamical instability before. This is still a pretty high rate, highly super Eddington. So likely most of this material is not accreted, but it's ejected from the binary and starts to create this CSM around the system. So if we now make this plot as a function of time until the delayed dynamical instability, basically for 1,000 years or so, we had been losing mass from the system at the order of 10 to minus 3 solar masses per year, which is much more than the winds of massive stars. And so we can see how this is tempting to use to try to explain this extended CSM that we may be seeing in the LFBOTs. And so now in the context of LFBOTs, we could start to put together a couple of stages of an origin scenario. The first stage would be the one we just talked about, is essentially stable mass transfer that keeps going for like 1,000 years or so. And this would be the one that creates the CSM that we see in radio observations there, right? But what happens next is that eventually the mass transfer becomes, I forgot I had this bit as well. We can be a bit more quantitative. Yeah, we can use our binary models. We know how much mass we lose as a function of time, so we can make predictions for the CSM profiles, right? And so in gray, thin lines, this is being done for individual binary models, but then the shapes are quite similar, so it makes makes sense to draw a mean line, which is this blue line here. And you can see that it has a couple of different regimes. So essentially on the right-hand side, this is the CSM that's created from the wind of the star itself, the low value. Here, the close part of the CSM is the one created by the massless once the mass transfer rate saturates as the thermal timescale of the massive star. And this is a very similar value for stars of different mass, different rays. It's a pretty natural prediction then. And at the slope at around 10 to 16, 10 to 17 centimeters, this comes from the phase when the mass transfer was starting. The rush slope overflow happened. And so this extension here is a combination of the thermal timescale of a massive star and the typical orbital velocity. So that's why you usually get this. And for comparison is the CSM density inferred from radio observations that we heard of for LFBOTs. Yeah, thanks. And this is sort of matching perhaps this tilt in the density profile. Okay, but then once we've done all this, then eventually the black hole will plunge into the remaining envelope of the star. At that point, the star already lost a lot of its mass. So we can think of it essentially as a compact blue supergiant or a main sequence star that already has a helium-enriched envelope as well a little bit. So the closest analog to this perhaps would be the mergers of two massive main sequence stars. And this comes from a simulation by Fabian Schneider that was done precisely in this context. And so we can see that you create this CSM, this nearby CSM that's going to come from this in spiral of a black hole in the residual envelope. You can estimate based on these simulations that the radial extent of the CSM should be something like 10 to 14 centimeters, maybe less. And it should also be to the point helium enriched and quite asymmetric. You can see that the density is mostly in the equatorial plane, not so much in the polar directions. Yeah. And then eventually we come to the point where the black hole reaches the helium core. At some point, it will tidally disrupt it to form a disk. And this is where we reach the central engine model that was proposed by Brian in 2022. And so we consider a disk that's going to be fit at a highly superconducting. It's going to be thick, and it's going to lose most of its mass before it actually gets to the black hole. So the velocity of the outflows from the disks depends on where in the disk you launch them. You know, most of the mass is going to be launched in the outer layers of the disk at the velocity of a couple of thousand kilometers. But the inner part of the disk could launch this polar jet-like outflow at a fraction of a c. That's then going to interact with the nearby CSM and power the optical and UV emission on the timescale of days, and then on the timescale of weeks to months, it's going to reach this extended CSM and give us the radio emission. Right? Now, I think the key point in this here is, you know, during the stage 2, I put this tensor mass here. That gives you the order of magnitude of how much mass you have in this nearby CSM around your accreting black hole. And so you might find it a little bit surprising how to get a fast transient that's embedded by so much mass, essentially. And I think this is the key point for these and similar models to really understand better. And so what we try to do here is really just to estimate what's the peak luminosity and the peak time scale of the optical UV emission, either by shock cooling emission or just the central X-rays being reprocessed. And the key here is what's really the diffusion timescale that's relevant for what we see. And so basically, even though we have so much mass, what we think could be happening is that when you have a very asymmetric CSM, what's really going to matter is the moderate amount of mass that you have near the polar direction. And so that could really shorten the rise time to the peak. We don't know what that is, but from scaling of these values, we can figure out that we need a few percent of the CSM mass to be near the polar direction when we're viewing, right? And so, but this is something that's really need to be resolved with actual models of how this geometry looks like, and maybe producing light curves, how Quentin was trying to go in that direction. I think that's the way to go. Okay, I'm not sure. I probably don't have time. We also did an estimate that the population statistic in terms of the rate and the metallicity preference seem to agree with what we find, what is being found observationally. But I'm just going to skip to my summary slide. Basically, there's this whole population of binaries with a black hole and massive star that also the other communities are excited about. Some of them will become LIGO sources probably, but many of them certainly will not. If they're not LFBOTs, they will be other transients as well. But we think that they could be a good candidates for a transient that has a lot of angular momentum from the binary orbit, and that is going to be embedded in an extended CSM. And hopefully in the future, we can keep developing those models to make better predictions as well. And that's thanks.
Great, thank you. Questions? Dan?
Can you say a little bit more about the rate? So I have always assumed that rates were kind of a hopeless constraint because all these common envelope things are so hard to predict. But what I had not realized was this link between binary black holes, which is now a rate we're going to understand very well. So there is actually a hope of this. So can you say a little bit more about that since you skipped over it?
Explain it better. I agree common envelope is difficult, but this is a little bit more convincing, I think, or less assumptions go there. So what we do here, right, we know from our binary evolution simulations which part of this parameter space would evolve to LFBOTs. In the future, we'll know observationally, hopefully, where the systems lie. Right now, we still do population synthesis to create those black hole massive star systems to the prediction. We have a bunch of variations, but long story short, we predict this range from 5 to 300, which is comparable with the range that was inferred. That's from Anna's Hoff paper, I think. It's going to get better. I mean, I'm showing the constraint on the binary black hole merger rate here, which is known very well. If we had this value for LFBOTs, I think it will be quite constraining. So hopefully.
Okay, thanks.
Yeah.
Hi, so this is very interesting scenario. Several key aspects are omitted, of course, because of the presentation was short. I would mention two things that came into my mind. First of all, this secondary black hole, while plunging into the star over a time scale of a few days, would necessarily accrete matter. So you can estimate the Bondi accretion rate onto such a black hole and think about some observable signatures out of this accretion process, different than a disk, X-ray, black body, whatever component. And the other thing is, how do you think, how likely is that the core of the star, this helium core, would collapse to form a compact object, and then those two would merge and emit these gravitational waves?
Right, yeah, thanks. On the point about accretion, there is some work proposing that maybe in this common envelope, like in spiral, it's only a small fraction of Bondi hole accretion rate, which would be a small fraction of the black hole mass in this case. But I think a key point, and maybe linking to some of the models for ultra-long GRBs that people were bringing up yesterday as well, is how much mass would be accreted from this disk that perhaps forms at some point. It could be a spectrum where when you have the accreting object is maybe a low mass black hole or a neutron star, it would need less mass to accrete to gain some spin. So perhaps that's the case where you would have a neutron star that spirals in through the helium core rather than tidally disrupting it into a larger disk. And that, in the mental picture that we're building, perhaps there could be a regime where you spin up this compact object and could launch a jet as well that could pierce through that, being relativistic rather than those here, and potentially link to some of the scenarios that people are developing for ultra-long GRBs, which I think would be quite exciting. But I'm no expert on this, so I'd like to talk with you as well.
All right, I think we have to move on. So thanks.
Thanks.
The session will be by Sahil Atri, who will be talking about late time polarization in the cow as evidence for long-lived geometric asymmetry.
Yes. So hello everyone, I am Sahil Atri, a PhD student at INEP OAR. So today I will be presenting my current work on 80-2018 cow. We had some old data that we had taken during this transient. So let's get started. So 80-2018 cow was discovered in like 16 June 2018 by Atlas survey. And you can see that the image after the subtraction, after subtracting the galaxy, and it has been found at a 63 megaparsec distance. And this has been one of the transients which have been observed a lot in the last decade. There are a lot of publications on this transient. And here are some of the key results, why it is weird. There has been a variable X-ray emission. There has been also bright radio emission. The spectra was featureless for starting 10 days. And after that, there was some broad features. And there was high polarization detection of 7%, which is one of the highest for any non-relativistic event. And there was a Nature publication where they detected a quasi-periodic oscillation at 224 hertz, which is a strong evidence for a central engine. And there has been also a persistent detection even after 5 or 6 years, which is very strange. So there is no single model which is able to explain all the properties. That is why it is very weird. And we are trying to solve this puzzle. We are trying to combine all the pieces and trying to find out what may have caused this transient. And with this effort, we have also tried to give our contribution through our data. We have observed this event with photometry, spectroscopy, and polarimetry. With photometry, we can try to understand the brightness evolution. With spectroscopy, we can understand the composition and kinematics. And by polarimetry, we can understand the symmetry of this event. This is the data set that we have acquired during this event. We have a photometry data from 2.5 to 80 days. We have a spectroscopy data from 2.6 to 60.5 days, and we have a polarimetry data from 17 to 28 days after the event. Since there has already been studies about the fitting of light curve, many people have already done it. We already know the temperature, velocity, radius, and luminosity of this event. So we haven't done it again because that will be just waste of time. So we have concentrated on the other things like spectroscopy. So as you can see, for the first 10 days, the spectra is featureless. And in our data from 13 days, we have started seeing some broad features. And by the end, at the last spectrum, you can again see there are only narrow features, maybe from the galaxy. So after that, we try to do the mission line fitting using simple Gaussian profiles. And we use some softwares like CurveFit and least square. We try to get the quantities like central wavelength, FWHM, we can call it velocity as well, and the equivalent width. We had a lot of data, but we wanted it to be dense. So I even requested Dr. Perley to send his data. And we did the emission line fitting even on their data and tried to plot everything on this plot. You can see on the first row, we have plotted the velocity evolution with time. And you can see that for some elements like hydrogen, the velocity is high. And for like H alpha, the velocity is really high in the starting and then it is decreasing with time. And for H beta as well, but the comparison to H alpha, the H beta velocity is a bit lower. And then in the second row, you can see the wavelength shift, how much the feature has shifted from its rest wavelength. And you can see that most of the events, most of the lines are red shifted. But they are not following a single trend. You can see that it is very weird. All of them are following some random trend, which may suggest that there are multiple regions involved in the ejecta. And also in the last, you can see the evolution of equivalent width. It is increasing in the intermediate time, and then it is decreasing again. Then we have tried to do another analysis. We have tried to get the equivalent width ratios of H alpha by H beta. In literature, you can find out these things, and even if you want to know more about the science of it, you can contact me later. So in a thin nebular state environment, you can see you expect H alpha by H beta to be 2.86, but in our case, this ratio is much higher and is normally equal to 6, which is equivalent to an Asian broadline region. Means the region is really thick and optical is dense and thick. Then we have tried to calculate another ratio, which is helium-2 by H alpha, which is generally less than 1 because it requires a really high energy to ionize helium, around 54.4 electron volt. So if we are getting such high ratio for helium-2, maybe there is something which, maybe there is some powering source which is producing such high energy photons, which is eventually ionizing this helium. And then we have also found the oxygen by H beta ratio, and we can see that the neutral oxygen is increasing with time, which may suggest that there is cooling and there is partially neutral material. So collectively, this tells us that the material around the source, the material around the transient is dense. There is a high powering source, and there is also a partially neutral material around. Then let's come to our polarimetric data. There has already been a publication on the polarimetric nature of 8028 in cow. they have detected a really high polarization of 7%, and then it is decreasing. In their data, the observations had really high uncertainty, so they have done the binning. So you can see the data is only till 15 days in their publication, but I tried to plot their raw data without binning, and also overplotted our data, which kind of fills the gap after 15 days. So we can see that the transient is polarized for around a month. So it follows an asymmetric nature for around a month. And then we have some preliminary results. One of our collaborators is working on it. And we have a spectropolarimetry from VLT Force 2. Right now, we don't know if this polarization is intrinsic or extrinsic. We are working on it, but just to show you, right now, we have considered both the cases. In this case, there is a polarization, and in another case, there is no polarization. We are still trying to find out if there is a wavelength-dependent interstellar polarization included in this or not. So right now, this is preliminary. And in the end, there are multiple models trying to explain 80-20-18 cow, like Central Engine may explain the X-ray variability and the late time observations and maybe QPO, but it struggles to explain the spectral features. Then there is tidal disruption event, which explains most of the things, but due to its off nuclear position and the spectral features we see, maybe there are some additional factors which has to be included here. And then there is CSM interaction, which explains most of the spectral features, but it struggles to explain the QPO detection and the late time detections after 5 years. And then there is a supernova, which generally follows a symmetry, but as we have seen, there are polarization detection of 7%. So this, in simple supernova case, it is also hard to explain it through a simple model. And the aim of this study is to just add some more observational constraints and help the community in knowing more about 80-20 cow. And maybe in the future models, these observations can also be considered when they make another models. So this is all I have. And thank you very much. If you have any questions.
Thank you. Any questions? Yep.
Hi, thanks for the interesting talk. One thing that I'm wondering is that the polarization that you've shown, well, it's not 1 or 2%, it can be even higher in some cases. And I've heard for some CSM interacting supernova, that can be a very dramatic effect between like the density, like along like a disk compared to the pole. Would this then perhaps mean that these LFBOTs may be viewing angle dependent? Perhaps if we see them edge on or pull on, then we would see something else. Perhaps they would not be LFBOTs if we see them from a different viewing angle. What do you think?
Yeah, actually, I haven't thought about it, but of course, as you said, the polarization depends on the angle from which we are observing it. So there can be, of course, this angle which we might study. Yeah, thanks.
See one. No, maybe I can quickly ask one then. So do you have any expectations for how the polarization might change with wavelength when you're doing the spectropolarimetry? Are there any predictions of that?
Right now, I am not sure about it because this work is done by someone else. But if there is a dominant axis and if the angle is stable, maybe we can say that it is intrinsic to the system. Otherwise, we have to still explain if it is zero, then there is something strange that how the polarization is increasing just after 1 day. So we are still working on it, and maybe you can contact us later and can let you know results.